by 2 times by 1.853 power 6 is equal to 5.813, okay, 5.813 times 10 to the power 6 millimeter power 4. Let me do it again. 2.1067 power 6 plus by 2 times 1.853 power 6 is equal to 8. Yep, 5.813 or 5.813 times by 10 to the power minus 6 meter to the power 4. Okay. So what we have just found is we have our Vy and Izz. Okay, I think we are ready to go. The only thing we have to do is the first moment of area. Okay, so I don't see any question for anyone yet. So we come over here. Okay. So the first thing we want to do now is we want to determine the shear stress at point A. Okay, we want to determine the shear stress at point A, and then I will copy, undo. I will copy the rules. Okay, and we're going to apply the rules. Okay, these rules are important. Okay, so the formula that we're going to use is shear xy at point A is equal to Vy over Izz, okay, Qz at point A divided by T. Okay, so we look at rule number 1. We know that Vy, regardless of the point of interest, right? V and I are constant. So we know that Vi is 90 times 10 to the power 3 Newton, right? Regardless of whether is it point A or point B. And then we now also know Izz is also a constant. So Izz we just found out is equal to 5.813. Okay, 5 times 10 to the power minus 6 meter 4. Okay. The next difficult part in this course is what is our QZA. Okay. So let's look at QZ at point A. Is equal to A y bar. Okay. So if you look at Z, right? Oh, sorry, you look at A. This is, I'm going to draw. This is the area that we have to find, the first move of area of this yellow section. Okay. Right. So we have to find that first move of area. So I like to do that. This is width multiplied by depth multiplied by y bar. And we already know where the global centroid is. Okay, so the global centroid is somewhere around here. Around here. Okay, so we know that the distance from here to here is 35 millimeters. So this is our centroid. Okay, so from here we know that this is equal, so our width is equal to 160. Our depth is equal to 20. The y bar will be 35 minus by 20 divided by 2. Why 20 divided by 2 is because the area of interest or the defined area centroid is exactly at the center over here. Okay. So this is where we have our 20 divided by 2. So from here, we calculate our first moment of area. So 35 minus by 10 times by 20 times 160 is equal to 80. 80 times 10 to the power 3 millimeter cube, or 80 times 10 to the power minus 6 meter cube. Okay, so we find our centroid. So from here, we can determine. Then the next thing is this: T is equal to twice multiplied by 0.02. Okay. Now, the question is, why use twice 0.02 and not 0.16? Right? You can see that. Yes? So if you look at point A, is exactly at the boundary of the flange and the web, right? Why we use this value? Okay, why use this value is because why did we use this value over here? Right? Is because when using twice, right? When using twice 0.02, okay, the shear stress xy will have a higher magnitude than using 0.16 meter, right? So you always calculate stress that has the highest value. Okay, you don't determine the lower value. Okay, pointless, right? So with this in mind, our shear stress at point A, right, is equal to 90 times 10 to the power 3 divided by 5.813 times 10 to the power minus 6 multiplied by 80 times 10 to the power minus 6, and you have to go twice 0.02. Why twice 0.02? Okay, because if we were to if I were to draw an arbitrary line over here, right, the shear stress will be carried on by this section over here, right, and also this section over here. So the shear flow will, so over here you have your V, right? The shear flow will go to left and right and then come down from here, right? So it splits between two of them. So that's why you divide by, or you consider twice the thickness of 0.02. So from here, so I write down here 0.02 is because of left and right webs. Okay, so this will be equal to 90 power 3 times by 80 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 30.965, right, times 10 to the power 6 Pascal. Okay, so that is at point A. So the next thing we're going to do is at point B. Okay, so we're going to look at point B now. Any question from anyone so far? I don't see. Stop me, okay? If you need me to repeat anything. Okay, as I say, this this lecture today is very important. Okay, unfortunately, only the three of you show up. Okay, you can ask me question live. Some of the rest can watch from the video. And those who of you who are just watching the video, you can also ask me question in the next lecture. Okay, I'll go through it again. Now, the next one is we want to find point B. Okay, so we know that the global centroid is over here. And we know that this is 35 millimeters. And this is our global centroid. So if we apply our rules, okay, so the rules, first rule number one is V and I are constant. Next, the datum is at the centroid. So this is our datum, right? And then rule number three said that the analysis starts from y max, or the distance further away from max. Okay. So the distance further away from it, so this will be our analysis direction. Why it's below is because the first moment of area cannot cross over the centroid. So in that context, this is the area of interest. Okay, this is the area of interest now. Okay, so now we are going to find our QZ. We're going to determine what is our QZ now. Okay, so we're going to determine QZ at point B. Okay, so what we are solving now is we are going to determine the shear stress at point B. Okay, we're going to determine the shear stress at point B. So we are going to do the Q Z at point B. So it will be width, depth multiplied by y bar. So this will be 2. Okay, the width is 20. The depth is 30. The y bar is equal to, so we know that this is 35, right? So the distance from here to here is equal to 100 minus by 35, which is equal to 65, right? So it's equal to 65 minus, right, 30 divided by 2. Why 30 divided by 2? The individual centroid, right? So the distance from here to here is 30 divided by 2. Okay. And then from here, the 2 over here is because of left and right webs. Okay. So this will be equal to 65 minus by 15 times 65 minus 15 times 30, 65 minus 15 times 30 times 20 times 2. The area, second moment, or the first moment of area is 60 times 10 to the power of 3 millimeter cube, or 60 times 10 to the power of minus 6 meter cube. Okay, so that is our QZ bar. So as I said, once the first moment of area is done, it is so easy, right? Then you just need to find the shear XY at point B now. Okay, so we know that this is equal to 90 times 10 to the power 3 our I is equal to 5.813 times 10 to the power of minus 6 multiplied by 60 times 10 to the power minus 6 divided by twice the thickness is 0.02. This is straightforward because B, the thickness is definitely 20 millimeters, right? It's not difficult at all. So this will be equal to 90 power 3 times by 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 30 power 3 times by 60 power minus 6 divided by 5.813 power minus 6 divided by 2 divided by 0.02 is equal to 23.223 or 2 to 4 times 10 to the power 6 Pascal. Now, I'm going to do another extra point, okay? And there are two ways of solving it.